hydrogen atoms are replaced by an alkyl group, giving rise to the primary, secondary and tertiary amines respectively. These are called aliphatic amines, while an amine in which NH2, NH or N group is attached to the aromatic hydrocarbon is called an aromatic amine. For example, aniline, in which NH2 group is attached to a benzene ring, is called an aromatic amine. Amines occur widely among proteins in the form of amino acids, vitamins, drugs, and hormones. For example, adrenaline, a secondary amine, is a hormone used for increasing the blood pressure. Quinine, an important anti-malarial drug, is chemically a tertiary amine. Thus, amines constitute an important class of organic compounds. Let us study various methods for the preparation of amines and their properties. Hofmann's method. When an alcoholic solution of ammonia is heated with an alkyl halide such as methyl iodide at 100 degrees Celsius in a sealed tube, all the three types of amines are obtained. The sealed tube prevents the loss of ammonia. To begin with, ammonia reacts with methyl iodide to form methyl N-amine, which is a primary amine. The reaction does not stop here. The methyl N-amine formed further reacts with another methyl iodide molecule, forming N-methyl methanamine. Two such similar reactions lead to the formation of N-dimethyl methanamine and finally tetramethyl ammonium iodide, a quaternary ammonia salt. The biggest limitation of this method is that it gives a mixture of amines which is very difficult to separate in the laboratory. At the same time, aryl halides do not undergo this reaction. Hence, aromatic amines cannot be prepared using this method. Reduction of amides. The primary amines can be obtained from amides by reduction with lithium aluminium hydride. Amides like acetamide, on reduction by lithium aluminium hydride solution in ether, give a primary amine, ethylamine, while under similar conditions, benzamide gives benzylamine, also a primary amine. On the other hand, N-methyl acetamide gives ethyl methylamine, which is a secondary amine. And N-dimethyl acetamide gives a tertiary amine, ethyl dimethylamine. The reduction with lithium aluminium hydride gives an amine having the same number of carbon atoms as the original amide. Hofmann's degradation method. An amide such as acetamide reacts with bromine and potassium hydroxide to give a primary amine, potassium bromide, potassium carbonate and water. The amine thus formed contains one carbon atom less than the parent amide. Similarly, benzamide gives aniline with one carbon atom less along with potassium bromide, potassium carbonate and water. It may be noted that this method produces only primary amines. Reactions of amines with nitrous acid. Consider a reaction between a primary amine like methylamine and a freshly prepared nitrous acid. During this reaction, NH2 group is replaced by OH from nitrous acid and alcohol called methanol is formed. Besides methanol, water and nitrogen are also produced. This nitrogen is seen as a burst of colorless and odorless gas. On the other hand, when a secondary amine such as dimethylamine is made to react with nitrous acid, a compound called nitrosoamine is formed, which is seen as a yellow oily liquid. Tertiary amines also undergo the reaction with nitrous acid. For example, trimethylamine reacts with nitrous acid and forms trimethyl ammonium ion along with nitrite ions. Aromatic amines also react with nitrous acid through the formation of diazonium ion. To conduct this test, take a mixture of aniline, which is a primary aromatic amine, and hydrochloric acid in a test tube, which is kept in an ice bath to maintain the temperature of around 0 to 5 degrees Celsius. Add some aqueous solution, sodium nitrite, NaNO2, to this mixture. Initially, HCl and sodium nitrite react to form NaCl and HNO2. HNO2, which is formed here, further reacts with amino group of aniline in the presence of HCl to form a salt called benzene diazonium chloride along with water. This reaction is called diazotization. Benzene diazonium salt produced here is commercially very important as it is used in the preparation of a series of organic compounds. We will study these reactions separately into the topics of Sand-Meyer reactions and azo coupling. Azo coupling reaction. In this topic, we will learn about azo coupling in detail, the reaction in which aromatic diazonium salts combine with another aromatic compound containing strong electron-releasing or donating groups is called azo coupling reaction. Consider a reaction between an aromatic diazonium salt like benzene diazonium chloride and another aromatic compound such as phenol. We know that phenol contains hydroxy group, which is a strong electron-donating group. Now add a few sodium hydroxide pellets to phenol to form a clear solution. This is kept in an ice bath to maintain a temperature of around 0 to 5 degrees Celsius. This cold mixture of phenol and sodium hydroxide is then slowly added to a freshly prepared cold benzene diazonium chloride solution. We know that benzene diazonium chloride is an electrophile. Here, hydrogen from para position in phenol is replaced by diazonium ion and a strong yellow precipitate of 4-hydroxyphenyl azobenzene is formed along with hydrochloric acid. Another example of azo coupling reaction is when benzene diazonium chloride reacts with aniline. Diazonium ion replaces hydrogen atom at para position in aniline and forms para-amino azobenzene. Thus, coupling reaction usually takes place at para position as seen here. However, in compounds like beta-naphthol, para position is blocked. In such cases, coupling takes place at one of the two ortho positions. During such reactions, hydrogen present at ortho position in beta-naphthol is replaced by diazonium group and a compound called 2-hydroxy-1-naphthyl azobenzene is formed. Summary: we've learnt about azo coupling, which involves a reaction between aromatic diazonium salts such as benzene
Preparation of aniline. objective. In this catalytic reduction of nitrobenzene, reduction of nitrobenzene by a metal hydrogen gas in the presence of a catalyst like finely divided nickel, platinum or palladium in ethanols to prepare aniline. Iron metal along with hydrochloric acid also reduces nitrobenzene to aniline. During this reaction, ferrous chloride is formed which further hydrolyzes to regenerate hydrochloric acid. Thus, only a small amount of HCl is required to initiate the reaction. A mixture of chlorobenzene and 2 moles of ammonia, when heated at 200 degrees Celsius and 60 atmospheric pressure, in the presence of catalyst cuprous oxide, undergoes ammonolysis giving aniline. Summary. We have studied 3
Hoffman bromamide degradation method. In this topic, we will learn the method of preparing primary amines by the Hoffman bromamide degradation method. A German chemist, August Wilhelm von Hoffmann. In this method, an amide such as acetamide reacts with bromine in an alcoholic solution of sodium hydroxide. This reaction leads to the formation of a primary amine along with sodium bromide, sodium carbonate, and water. Note here that during this process, the alkyl group which was attached to the carbonyl group of the acetamide has now migrated to the nitrogen atom of the amine. Therefore, the amine thus formed contains 1 carbon atom less than the parent amide. Similarly, benzamide gives aniline with 1 carbon atom less along with sodium bromide, sodium carbonate, Summary. Similarly, benzamide gives aniline with 1 carbon atom less along with sodium bromide, sodium carbonate, and water. It may be noted that this method produces only primary amines. Summary. Physical properties of amines. To study some important physical properties of amines such as polarity arises due to the more electronegative nitrogen atom, which pulls the shared pair of electrons away from hydrogen. This polarity results in intermolecular hydrogen bonding among primary and secondary amines. Tertiary amines do not have any NH bond, and hence no hydrogen bonding takes place among them. Due to this hydrogen bonding, primary and secondary amines have higher boiling points than non-polar compounds such as alkanes of comparable molecular mass. On the other hand, when compared to alcohols, amines show lower boiling points. This is because hydrogen bonding in alcohols involves oxygen atom, while in amines, a nitrogen atom is involved. We know that the electronegativity of oxygen is higher than that of nitrogen. Hence, hydrogen bonding in alcohols is stronger than in amines, and therefore it takes more energy to break these bonds. This makes alcohols boil at higher temperatures than amines. For the same reason, amines also have lower boiling points than carboxylic acids of comparable weight. Solubility. Lower amines are soluble in water because they can form hydrogen bonds with water molecules. However, higher or complex amines are insoluble in water. Their long complex hydrocarbon chain, being hydrophobic in nature, interferes with hydrogen bonding, making them insoluble in water. Similarly, aromatic amines such as aniline are not very soluble in water due to the presence of the hydrophobic benzene ring. Amines are also soluble in less polar solvents like ether and benzene. Summary. We've learned that amines are polar compounds. Basic nature of amines. You must have observed vinegar or lemon juice being applied on basic nature of amines. You must have observed vinegar or lemon juice being applied on seafood to reduce its distinctive fishy odor, which is caused by the presence of amines in it. We know that chemically, vinegar is an acetic acid. It reacts with the amine from the seafood and neutralizes it. This shows that all amines are basic in nature. The strength of an amine as a base depends on the ability to accept a proton from an acid to form ammonium salt. In this topic, we will learn about the basic nature of amines and will also compare the basicity among different classes of amines. Amines are very reactive organic compound due to the difference in the electronegativity between nitrogen and hydrogen atoms, as well as the presence of lone pairs of electrons on nitrogen atom. Due to this lone pair of electrons present on nitrogen, the amines behave as nucleophiles. The number of hydrogen atoms attached to nitrogen atom also decides the course of reactions of amines. Therefore, the primary, secondary and tertiary amines differ in many reactions. Let's discuss the basic nature of the three classes of amines in the gaseous state. For this, consider methyl, dimethyl and trimethyl amines as examples of primary, secondary and tertiary amines respectively. Methyl group is an electron-releasing or donating group. This means it pushes shared pair of electrons towards nitrogen atom and increases the electron density on it. This increases the ability of nitrogen to accept a proton. Thus, basic character in aliphatic amines increases with increase in alkyl substitution. The basic nature of aliphatic amines follows the order tertiary greater than secondary greater than primary in the gaseous phase. However, in the aqueous phase, the order of basicity changes. Trimethylamine, a tertiary amine, is a weaker base than a primary amine. This is due to steric and hydration effect. The steric effect refers to the crowding of methyl groups around the nitrogen atom, which hinders the attack of proton on the amine molecule. Hydration energy is the energy released when water molecules form hydrogen bonds with protonated amine. The greater the extent of hydrogen bonding, the greater is the stabilization of amine and the greater is its basicity. As you can see, due to the overcrowding methyl groups, hydrogen bonding does not take place easily in the tertiary amine. Hence, in a tertiary amine, hydration energy is minimum, steric hindrance is maximum, and therefore it is least basic among all amines. Reactions of amines with water and acids also confirm their basic characters. All three classes of amines react with water to give quaternary ammonium ions. Consider a reaction between a primary amine such as methylamine and water. Initially, water ionizes into H+, leaving behind its shared electron on oxygen atom. H+, being an electrophile, gets attracted towards the lone pair of electrons present on the nitrogen of amine. This results in the formation of positively charged quaternary methyl ammonium ion. It should be noted that the initial loss of a proton from water leaves behind hydroxide ion. This makes the solution basic. The basic nature of amines can also be seen during their reactions with acids. Consider the reaction between ethylamine, a primary amine, and hydrochloric acid. Hydrochloric acid first splits into hydrogen and chloride ions. H+ ion then attaches itself to nitrogen atom from the amine, and the lone pair present on nitrogen is shared between them through a coordinate covalent bond. A positively charged ethyl ammonium ion is thus formed. It attracts the negatively charged chloride ion which is formed earlier due to the dissociation of HCl, and a salt called ethyl ammonium chloride is formed. Thus, like all other hydroxides, amines react with mineral acids to form salts. This shows their basic character. Summary. To conclude, we can say that the basic character of amines is proved by the fact that they react with water to form basicity of aryl amines versus ammonia. Nitrogen atom has 5 valence electrons in its outermost shell. 3 of its electrons are used in bond formation during formation of ammonia. Thus, the molecule formed has 1 active lone pair of electrons present in a sp3 hybrid orbital. 1 active lone pair of electron of ammonia is readily available, hence it accepts a proton from a water molecule and behaves as a base. Basic character of ammonia can be better understood in terms of its pKb value, which is 4.75. Now, if one of the hydrogen of ammonia is replaced by a benzene ring, it is called aryl amine or aniline. Will there be any change in its basic strength? In this topic, we will compare the basic strength of ammonia and aryl amine. Now let us observe the pi electron cloud of aniline molecule. There is a pi electron cloud above and below the plane of aromatic ring. Here, the NH2 group is attached directly to sp2 hybridized carbon of the benzene ring. At the same time, the orbital of nitrogen containing the lone pair of electron is close and almost parallel to the pi electron cloud of the ring. Because of this position, the lone pair of electron can interact with the electron cloud of the ring, transferring a part of its electron density towards the benzene ring. This can be also illustrated by observing its contributing resonance structures, in which the lone pair of electron of nitrogen transfers to 2nd, 4th and 6th carbon of benzene ring. Structures 2, 3 and 4 clearly show that electrons are delocalized from nitrogen atom towards the ortho and para positions of the benzene ring. So the active lone pair of electron is not available readily, hence aniline cannot bond to hydrogen ion as effectively as ammonia. That is why aniline is much weaker base than ammonia. This can be confirmed by comparing pKb values of ammonia and aniline. Higher value of pKb for aniline suggests that it is much weaker base than ammonia. Summary: one active lone pair of electron of ammonia is readily available, hence it accepts a proton. Separation of primary, secondary and tertiary amines. A mixture Separation of primary, secondary and tertiary amines. A mixture of primary, secondary and tertiary amines reacts with benzene sulfonyl chloride, called the Hinsberg reagent, to give a mixture of primary and secondary sulfonamides. Here there is no reaction with the tertiary amine. On addition of dilute hydrochloric acid to this reaction mixture, the unreacted tertiary amine dissolves. However, the mixture of secondary and primary sulfonamides remains insoluble. This mixture is obtained as a residue on filtration, and the filtrate on neutralization gives the tertiary amine. On adding an aqueous solution of potassium hydroxide to the residue, the primary sulfonamide dissolves, but the secondary sulfonamide remains insoluble in it. After the filtration of this reaction mixture, the filtrate on neutralization gives the primary amine, and the residue on neutralization gives the secondary amine.
Alkylation and acetylation of amines. Amines, both aliphatic and aromatic, undergo a variety of substitution reactions such as alkylation, acetylation, etc. During these reactions, hydrogen atom or atoms of amines are replaced by different substituent groups. In this topic, we will study alkylation and acetylation of amines. Alkylation. A primary amine, such as ethylamine, reacts with an alkyl halide like methyl iodide and undergoes a substitution reaction. The nitrogen atom of ethylamine functions as a nucleophile, and hence it shifts its lone pair of electrons towards the electrophilic carbon of methyl iodide. As a result, the nitrogen atom becomes positively charged. Simultaneously, the iodide group of methyl iodide leaves as iodide ion, which deprotonates this positively charged nitrogen, and a new compound, secondary methyl ethyl amine, is formed. As in this case, hydrogen gets replaced by an alkyl group. The reaction is known as alkylation. Acetylation. Let's take the example of an aromatic amine, such as aniline. Here, the nucleophilic nitrogen atom of aniline shifts its lone pair of electrons towards the electrophilic carbon of acetyl chloride. Simultaneously, the pi electrons of carbon-oxygen double bond shift towards the more electronegative oxygen atom. Thereafter, carbon-oxygen double bond is reformed and the chloro group is pushed off as chloride ion, which then deprotonates the positively charged nitrogen atom. This results in the formation of acetanilide along with hydrogen chloride. This reaction reaction is called acetylation, as hydrogen gets replaced by an acetyl group. Summary. We have studied the mechanism
Tests to detect amines. Objective: to study some of the reactions which are used to detect the presence of amines, particularly primary amine. It is a characteristic reaction given by the primary as well as secondary amines when they react with carbon disulfide. Take a mixture of ethyl amine and mercuric chloride in a flask. Add some carbon disulfide to it and heat gently. Both the hydrogen atoms of an amine are replaced by the CS group, and ethyl isothiocyanate is formed along with mercuric sulfide and HCl. The ethyl isothiocyanate, which is formed here, smells similar to mustard oil, and hence this reaction is known as the Hofmann mustard oil reaction. Tertiary amines do not give this reaction. Carbylamine reaction. Let's now study a reaction which is given exclusively by primary amines and hence is used as a laboratory test to identify primary amines. In this reaction, a primary amine such as methylamine is heated with chloroform and alcoholic caustic potash. The reaction gives an isocyanide or carbylamine called methyl carbylamine along with potassium chloride and water. The carbylamine which is formed here has a characteristic nauseating odor which makes the primary amine easy to detect when using this reaction. Besides the carbylamine test, another reaction which is used to detect primary amines is their reaction with aldehydes forming Schiff's base. To perform this reaction, add acetaldehyde to a solution containing methylamine and hydrochloric acid, which is present as H+ and Cl- ions. Acetaldehyde is a polar molecule having delta+ charge on its carbon atom, while a slightly negative charge on its oxygen. Methylamine, with its lone pair of electrons present on the nitrogen, acts as a nucleophile and thus attaches itself to the positive carbon atoms of the acetaldehyde. This nucleophilic addition results in shifting a pair of electrons which was earlier shared between carbon and oxygen. The oxygen now becomes negatively charged due to the extra pair of electrons on it. Furthermore, proton transfer takes place within the molecule. During this transfer, a proton from an amine is lost and is taken up by the oxygen, and one of the lone pairs is shared with it. The oxygen now has two lone pairs of electrons. Out of these, one pair is shared with the incoming hydrogen ion, which is present in the solution as hydrochloric acid. The molecule further loses water and an H+ ion, forming a hydronium ion, and a compound called Schiff's base is formed, giving a magenta-pink color to the solution. Thus, the presence of a primary amine is confirmed by the change in color of the solution from colorless to pink. To summarize, we have studied the following three